So this is Fun with Profunctors. I'm going to be talking about, let's see. I'm going to try and give a bit of an overview of Profunctors first of all, just to give a bit of background. And then the thing I really want to talk about is this Profunctor lenses idea. So if you're familiar with the lens library from Haskell, it's sort of a different sort of development of those ideas. Lenses, prisms, traversals, all those kinds of things. If you're not familiar with the ideas from Haskell lens library, I'll try to give a quick primer on lens before we get too deep into this. So the thing that is kind of interesting about this is that I think it gives a really nice, clear presentation of, or at least clear representation of the lens ideas. But it hasn't really been developed in the Haskell lens library, or as far as I know, in the Haskell library at all yet. So Edward Komet, I think, is a little reluctant to develop the lens library this way because it sort of pulls in a lot of dependencies that are relatively non-standard, like non-base dependencies, like Profunctors, for example. So the way I came to find out about these ideas was by working on the PureScript lens library. And Edward popped up and said, you know, you really ought to take a look at this Profunctor lens idea. You don't sort of have the same set of restrictions that we have in Haskell. So we tried it out and implemented it. It was very clean and elegant, and I think it's sort of like a nice overview of like lens ideas, and I wanted to cover it. But most of the sort of material here is sort of extracted from the Haskell Lens IRC channel and various other places on the internet. There isn't, as far as I can tell, a really sort of clear presentation of this stuff. So you know, hopefully this will serve as a nice introduction, but we'll see. I have quite a lot of material, so we'll just sort of see how much I get through, but please do stop. It's quite dense, so please ask a lot of questions. If something isn't clear, I'm sure somebody else has the same question. Okay, so let's just go through the primers, prerequisites real quick. So we're going to look at various types of functor. So a profunctor, as you would expect, is related to the functor type class, which hopefully we all sort of know and are familiar with. So a functor is a type constructor f, and you have an fmap function that gives you a function from fa to fb whenever you have a function from a to b. So a good example of this is the map function on lists. So if you give me a function from a to b, then I can give you a function from list of a to list of b, where I just apply that function pointwise at every element in the list. Okay. So people like, you know, analogies for things like monads and functors, and the typical one is a burrito. So I have this burrito functor here, and it's got some type argument, which is the filling. So if you can give me a way of transforming one filling into another filling, then I can transform your burrito into the other type of burrito by taking off the tortilla, applying your function to the filling, and then putting it back in the tortilla, right? So this is sort of our typical, this is going to be our basic example of a functor, okay? As I say, stop me if anything needs, because like I say, this is going to get pretty dense pretty quickly. So, okay, so then sort of related dual idea to a functor is a contravariant functor. So we say a functor is covariant, and we have this other idea of contravariant functors. And if you're familiar with sort of Java and I guess subclassing and these ideas, then you'll have heard the words contravariant and covariant, and they are related. This idea of sort of things being sort of depending in the same way, or depending in sort of a reverse dependency sort of way. But so contravariant, instead of having this fmap function, has this cmap function.
So are normal functors covariant?
So normal functors are covariant, yeah, that's right. So covariant just means, so the co sort of, I guess, meaning together, right? Like the arrows sort of go together in the same direction. It's a to b and f of a to f of b. But in the contravariant case, they go the other way around. We flip the arrows on one side, right? So we have an a to b, but now I have an fb, and I give you back an fa, okay? So a sort of simple example of that might be, you know, like a customer functor. A customer, instead of a burrito where we're wrapping up a burrito, now we're sort of taking we're wrapping up a filling. Now we're taking the filling and we're doing something to it, right? We're going to have this eating action. So if I can take this filling and eat the filling, then the customer type constructor is now contravariant, okay? Because if I can give you a function from A to B, and I have a customer that's willing to eat B's, then I also have a customer that's willing to eat A's, because I can just transform the A's into B's and give it to the customer. Does that make sense? Okay. So this type of functor where you have...
How do you know which... So you know how to go from A's to B's.
Yes.
But does that imply that every B has some A that goes to it?
Not necessarily. So that'd be like, I guess, a surjective function or something, right? I think not necessarily, no.
So then how do you define the f of B to f of A function?
So I mean, here's an example, right? It's specific to the f that you pick. So here's an example, like for the customer. If I have an eat function that takes, let's see, that will be it's an f of b, so that's going to be a b to an IO.
Wait, the filling is A or B?
Okay, so you have to do a bit of sort of substitution in your head here. I'm sorry, right? So here f is going to be your A to B. Okay, and we've picked. I'm sorry, it doesn't help that this is also called f, but this f is going to be customer, right? So now we have a customer of b, right? So we have a customer who will eat b's, and we have a function from A to B, and I want a customer that will eat a's. So I just take all my a's and I apply f to them to get a bunch of b's, and then feed them to my customer.
Wait. This might be easier.
The burrito analogy doesn't like generalize nicely.
I don't understand it.
Yeah, I think
So
Okay.
if you only eat cooked food, and I have some uncooked food, I have a function that cooks the food, then I have a way to feed you.
Right, but that's a function from uncooked food to cooked food. And you're talking about going from a person who eats uncooked food to a person who eats cooked food, right?
So I have a way to feed people who eat uncooked food, because I have uncooked food already. In order to also have a way to feed people who eat cooked food, I need to cook the food.
That looks like covariance to me, not contravariance.
So it's not necessarily that I have a way to feed them. It's that I can eat the food, right? If I can eat, what was your example? I'm sorry. If I can eat cooked food, then I can eat uncooked food because I can cook it and then eat it.
I think it might be helpful if you could just write out the specific type of CMAP on the board with the customer.
Yeah, let's do that.
There is a whiteboard.
Oh, good. Good idea. All right. So.
Maybe, so the camera, if you rotate the board, you'll be on the camera. Although, well, you've got an audience to worry about too. Never mind.
Yeah, this should work.
Okay.
So if we have some contravariant functor C, okay, but we're just going to pick that to be customer, okay. So.
The one you read on the board is code.
Yes, it is. I'm sorry. Thank you. Okay. So I have a customer of B. Customer of A.
Yeah.
Okay, so let's pick this to be a cooking function. Okay, so this is, we have some uncooked. Okay, then I should be able to take a customer who is willing to eat cooked food, and you should be able to give me a customer that is willing to eat uncooked food.
Yeah, so how do you do that?
Okay, so you take the food. If you're given a piece of, so let's write out the type of customer. Food is food to, let's say, some action, IO action. Okay. So we'll fill in the blanks. Okay, I'll just call it un and co or something.
So the customer is not a wrapper for food, it's a function that transforms food into an IO action.
Correct, yeah. Okay.
Wait, so un is what?
Uncooked to cooked.
Okay.
Then I can, if you have an action which will accept cooked food, then I can give you an action eat which will accept uncooked food, because I can cook, and then I just compose these two things. It's just function composition.
So the type parameter is describing the requirement and not necessarily what it's spitting out. That's why we can do it? Is that why?
So not sure how to explain this again. So maybe I need to skip ahead a slide or two and just continue, and it'll become clear. So the sort of the key example is like the function arrow, right? So the function arrow has two type arguments. It has its arguments and its return value. Okay, so we say it's covariant in its return value. Okay, because if you have a function which returns A's and an A to B, then I can just compose them and I get a function that returns B's. Okay, but it's contravariant in its argument, because if I have a function from A to B, I need an A and I have to map this way, right? I have to have a sort of a Z to an A to a B, then I can get a Z to a B. So it maps the other way.
Okay, can you draw that?
Yeah.
There's probably some laws that would make this more clear, right, between covariant and contravariant.
So there are contravariant functor laws, which is just the functor laws, the other way around. This is sort of my archetypal example of a contravariant functor. So it's sort of trying to think of a better one, but I mean the function arrow is sort of a typical one. Let's see. So I have A to B. Okay, so let's say I want to write an instance of functor for the second argument. Okay, so let's say we fix the first argument, and we want to show that it's functorial in this piece. Okay. Okay. Then, well, let's give a type signature to fmap. Okay, so fmap says if you give me an x to a y, then I give you an f of x, so that's going to be a to x. Okay. Then you give me an f. You'll get an f of y back. Okay, so that's an a to a y. Okay, so we need to implement this. Well, that's just function composition, right? If we call this f and this one g, then we do f first and then we do g, then we get a to y.
Sure.
Okay. So I'll write that. It might be the other way around. No, that's correct, right?
Is that the dot?
That's composition, yeah, sorry, dot. So let's say we want to write a contravariant instance, okay. But now my claim is that it's contravariant in this piece, right? So, so let's write out the signature again. So we had CMap, and we needed an A to a B, and then a C of B. So a C of B is a, oh, I'm sorry. Alpha renaming in my head is not working. All right. X to a Y, let's say, and a C of Y, so that's a Y to a B, and you need to give me a Y to an A.
Wait, a C of Y is a Y to B?
So we're just plugging in, this is C of
Okay.
Y, and we're just plugging in Y here. Oh, this is an X, I'm sorry. Okay, and again, this is just function composition.
But you compose them in the other
That should
way.
be x to b.
Yes, it should, thank you. Okay, so this is just function composition again, right? If I have an X, and I have an X to a Y, and a Y to a B, then I can put the X into the first function, get a Y out, the Y in the second function, get a B and return it. So I think this is like,
Okay, so you're just composing them the other way.
yeah, so this is flip compose.
Yeah.
Okay,
Alright.
you can always extend a function by applying. You can take your function and sort of apply it on the right and extend the sort of chain of functions, or you can take a function and apply it on the left. But in doing so, you have to flip the type arguments. Does that make sense?
This is just the generalization of the customer.
Right. So exactly. So a customer is a function, right? Here we're just fixing B to be IO.
Okay.
So now we just have one type argument. I was saying, so this filling here is the one on the left of the function arrow. That's this one. It's contravariant. So we're saying we're contravariant in filling. Okay.
Cool.
Any other questions on that before I carry on?
I can't imagine where I would use contra.
Right. It's not as common. It's not nowhere near as common as functor in my experience. It's more common, I think, in the form of a profunctor, which is the next slide. After this one. So an intuition for this is, so we already covered the function arrow, right? So we jumped ahead a little bit, but a functor is something where the type argument appears only in what we call positive position, okay? And something is contravariant when its type argument appears only in negative position. If you have a mix, you can't be either, okay? So what does positive and negative position mean? Well, something is positive if it appears on the, let me get this right, left-hand side of an even number of function arrows. Okay, so let's write this out. So it's easy to see when see it with the function arrow. Okay, so here's A to B. Is this? Well, I'll tell you the answer for these, and then we'll carry on. Okay, this is a positive occurrence of B, and this is a negative occurrence of A because we have A on the left-hand side of one arrow. Okay. Would anyone like to guess what the polarity of C is in this type? Positive. B? Negative. A. Also negative, right? And if it's not clear why A is also negative, think of it like this. Okay, you can always curry these things. Uncurry, actually. Okay, let's do a more interesting example. So we had A to B to C. If I parenthesize like this, okay, this is still positive because it's on the right-hand side still. But this has changed, right? So in this case, B is negative because it appears on the right-hand side of one function arrow, left-hand side of one function arrow, which is this one. Okay, so every time you go into a function arrow on the left, you flip the polarity, okay? This one is positive. So this went, because I went inside two function arrows on the left, I flipped twice and now I'm positive again. So A is positive, right? So the rule is I can make a functor when the type argument only appears in positive position. So if I want a functor for something like, let's see.
Is there some other definition of positive and negative positions? Because that rule with the arrows, I can believe you that corresponds to something, but I don't really know what it's supposed to correspond to. Like, where does it come from? The arrow rule.
The rule with sort of positive and negative when you
count arrows. Why are you doing that?
Oh, I can't sort of give a good argument, but like, so if you sort of, sorry, what were you saying?
Oh, I said the reason why we have to distinguish positive and negative is because we use it for profunctors, right?
So in this case, yes, we are going to use it for profunctors, but I'm just trying to give an intuition for sort of what constitutes a functor versus a contravariant functor versus neither. But so if you buy the idea that like the left-hand function argument involves this flip of the type argument somehow, then every time you look at a function argument as opposed to a return value, you have to perform this flip, and the positive and negative thing is just essentially saying whether or not my type argument varies covariantly or contravariantly. We're just sort of tracking the same thing a different way, but the counting argument is just taking care of this the strange behavior of the left-hand side, if you like, different behavior.
Why do we flip? Can you clarify or provide some intuition related?
So every time you go onto the left of a function arrow, you have to essentially there's sort of like if you want to write an F map for this, let's say, a functor instance, every time you go to the left of a function arrow, you essentially have a contra map, like a contravariant map that you have to apply to the left-hand function argument here. Okay. If you have two contravariant maps, then that's the same as just applying a function, or rather, it's the same as an F map for some functor, right? I don't think we need to sort of go into too much detail on this. Like this, just sort of trying to build an intuition. So the point is, I said this was positive and this was positive, so this one was negative. So, for example, then you can build a functor for this because in A, because every A appears in a positive position. There's one A here that's positive, and there's one here that's positive. Okay, so you can write a legitimate functor instance for this, and it actually turns out this is a monad as well, and I think it's called the search monad or something. It's related to the continuation monad, but you can keep going, right? And you can add more type arguments as long as you sort of only keep the ones that occur in positive position. So, but the point is, so you can't make a functor, for example, for this, where there's also an a here, okay, because that appears in negative position. So that would be like trying to write, here's a simpler example, right? So I claim that you can't write a functor instance for this. And the reason is that a appears in a negative position. Okay, so if we try to write an instance for that, we'll see where it goes wrong. Okay, so the type of fmap for that proposed functor would be this. Oh, I'm sorry. I'm in Haskell. Okay. Okay. Well, in this case, actually, you can implement that because you can just always return true or something. So let's fix this to be some abstract type. So if you have some function from an a to a b and a function from an a to an x, and I give you a b, you can't produce an x in general because you need an a to produce an x. And I can't produce an a using this. Okay. So you can't write a functor instance for the left-hand side of the function arrow, but you can write a contravariant instance for it. So in general, if you have a mix of these positive and negative occurrences of a type variable, you're not going to be able to write a functor instance, and you're not going to be able to write a contravariant instance. So then a profunctor you can sort of think as a solution to this. We have, let's see. Okay, I have one more set of things to get through. So in invariant functor is sort of another it is a way to sort of mix these ideas. Okay, so if I can't, let's say if I had a mix of positive and negative occurrences of this type variable, if an a to a b wasn't enough to perform this mapping operation, then maybe if I put in the function in the other direction, okay, then maybe combined they're enough to perform this mapping operation. I can take my positive occurrences and I can use this function to map covariantly, and then I can take the negative occurrences and I can take what I had in the contravariant case and I can use that to map over the negative occurrences. Okay, so here's an example. So here's a functor a arrow a. And no, we know that we can't write a functor instance for this because there's an a in negative position. That's this one. And we know we can't write a contravariant instance because there's an a in positive position. But we can write an invariant instance. So we take these two functions. So we have an f that's mapping forwards, g that's mapping backwards, and we just compose. It turns out this composition of three functions turns out to be the thing that you need. Okay. So invariant functors aren't used all that widely. So what can we do with them? Not very much, but here's one operation that you can do. So if you have an isomorphism between a and b, so an isomorphism is a pair of functions that are inverse to each other. So we have a function from a to b, and then we're able to turn it around and invert it. Okay, so we have a function from b to a, and these things should cancel each other out, right? So if I take an a and I apply the first function and get a b, and then I apply the second function and go back to an a, I should get the a that I started with. And similarly, if I start with a b and go to an a and go back to a b, I should get the b that I started with. Okay, so that's an isomorphism. If I have one of those and an invariant functor, then I can take this isomorphism and I can lift it over an f of a to give me an f of b. So how do I do that? Well, I take my forward direction from my isomorphism and my backwards direction from my isomorphism, and I just do this IMAP operation. So remember IMAP took two functions. So this is exactly what's packaged up inside my isomorphism class, okay? So if you look at this looks a little bit like a funny variant of like a map operation, right? But where my function on the left-hand side is a whole isomorphism now. I had to sort of strengthen the idea of what a function was to an isomorphism to be able to do this mapping operation.
Can we make a use of this in like serializing, deserializing?
Mm-hmm. Yes. There's a paper called Rotten Bananas, actually. You're familiar with like the banana barbed wire lenses paper? So it's about recursion schemes, but you can generalize it to these invariant functors, and they talk about how you can use them to express parsers, but then because everything was invertible, you can turn it around and get a pretty printer too. Or a serializer, deserializer. Okay. So invariant functors aren't generally used very much. You don't see them very often. They turn up in Scala Z, I think. They're quite tricky to work with in general. It's not clear immediately how to generalize things like the applicative and monad hierarchy on top of functor to invariant functors. And generally they're tricky, I think, because if you want to map, if you have to provide both functions, the one direction and the other direction. It's not always obvious how to turn a function around in order to be able to apply this mapping operation. So the profunctor approach and the profunctor class solve this in a different way. So instead of having one type argument that can appear in positive positions and in negative positions, we split it into two type arguments. So you have one type argument that's dedicated for all the positive occurrences, and then a second one which is dedicated for all the negative occurrences. Okay. So here's a profunctor. So we have this die map operation, and there's a nice motivating example here, which is the function arrow. Okay. So if now again, just like in the invariant case, I have two functions. I have an a to a b and a c to a d, and now I can map covariantly in my first argument. Contravariantly in my first argument with this function here. So I can take a b and I can turn it into an a. So that's reversing this arrow. And I can map contravariantly in my second argument, so I can take a c to a d, and that's what I have in this argument. Okay. So this is saying, if I give you this function that can handle all the negative occurrences, and I give you this other function that can handle all the positive occurrences, then you can sort of map over the b, which is your negative stuff, and the c, which is your positive stuff. Does that make sense? Okay. And then the sort of typical example is the function arrow, and I said that the function arrow has negative appearance of a type variable, which is its argument, and a positive occurrence, which is its return value. Okay, so that's a good category for a profunctor, and it turns out you can write it using, again, this sort of like triple composition. Okay. All right, so that we got through quite a lot there. So are there any questions on that stuff? Yeah.
My intuition tells me that this is going to be used for searches, because you're looking for things, and this is a way to basically skip over a lot of details.
So there are so the profunctor is has a lot of instances. Okay, because so the restrictions that you had on functor and contrafunctor are relaxed. It turns out there's a great number of instances, and some of those are related to searching. Actually, I'll show a little bit about that towards the end. I'm not sure if it's going to be exactly what you're thinking of, but
well, it's very
I think it's
exciting
related.
to hear you talk.
Okay.
So can you go back to that for a second?
Sure.
The K there, is that the profunctor?
Okay. Yes. So I said I'm picking p to be the function arrow. So if we substitute here, then I've got a function from a b to a c, and I've got a function from an a to a d. We can write it out. Okay. So I've got 4 functions I need to compose. So that's why we have 2 compositions, right? So I have an a to a b, a c to a d, a b to a c, and an a to a d. Sorry, I need to get an a to a d. Okay. So I have an a, I plug it into here, I get a b, I plug it in, I get a c, plug it in, I get a d, and return it. And that's why you have 2 compositions there. Okay. So what can we do with profunctors? So an awful lot, actually, or at least once you generalize them a little bit, or specialize them rather. So we get, because it was so similar to this invariant idea, this invariant functor, we can also have, we also have this isomorphism lifting idea. Okay, so if we have an isomorphism from A to B, or between A and B, so before I had just an invariant functor applied to A, now I need to split out I've split out my positive and negative occurrences, right? So I just fix them to be the same. I have a P of A and A, okay? And then I can get back a P of B of B, okay? And again, I have this die map operation. I just apply one direction of my isomorphism in one direction and the other direction in the other direction, okay? And the reason I can do that is the right-hand side is covariant, so I can apply the isomorphism forwards and I get an A to a B. And the left-hand side is contravariant, so I can apply the reverse direction of my isomorphism contravariantly, okay? So my function, my reverse direction of my isomorphism is a B to an A, but I apply it contravariantly and I get an A to a B. Make sense?
Wait, To and from. What are to and from?
Oh, those are the packaged up functions that make up my isomorphism.
But is to an A to A?
To is an A to a B.
And from is a B to an A?
Sorry, this is the. Sorry. A to B is contravariant. So from. I actually think I got these the wrong way around. From. I think these are the wrong way around. Sorry. It should be iso from to. Okay. So I'll write some code in a second and hopefully be a bit clearer. Okay. Actually, let's just write these out. So here's data.profunctor loaded up. Let's see, we'll do info on profunctor. So we have this die-map operation here. Okay. Is this readable, by the way?
Yes.
Bigger? Okay. So this is the function that I had on the slide, right? So I have something that acts, this A to B that acts contravariantly in the first argument, and C to D that's going to act covariantly in the second, and I can take a PBC to a PAD by applying each one, okay? So let's see. I want to give an example. We can just implement this. Okay, so if I import data.tuple, we have this function called swap. It takes a tuple and it just reverses the order of the arguments, right? Just flips them around. So I'm going to do swap of 1 and hello, something, and get hello 1. Okay. So if I look at the type of die map and I apply it to swap twice, okay, then that gives me this. Okay, so this says if you pick a profunctor, P, then I can swap the first argument and get an B to an A and get an A to a B, and I can swap the second argument. So these obviously act the other way around, right? But you get an A1, B1 and map covariantly and get a B1, A1. Okay. And then you can write more interesting things, right? So you can write something that reassociates 3 things in a triple. Okay, so you can say if I have an A and a B tupled up, and I tuple that with a C, then I can turn that into an A tupled up with a tupled up B and C. And I can do that just, so these things are isomorphic, right? That's the sort of observation, right? It doesn't matter what order. Essentially, there's the same data content in 3 things, no matter how you triple them up. And if I want to witness the fact that they're isomorphic, I have to provide 2 functions. One that's inverse to the other, going in both directions, right? Like provide evidence for the fact that they're isomorphic, yeah. So if I have a triple like this arrangement, an A, and then the right-hand side is tupled up, then this is a function that takes me to the other arrangement, right? I just rearrange the brackets. And then this is literally just the flip of the function we have on the left, right? We take, again, we're just rearranging the brackets. But these are definitely inverse to each other, okay? Like syntactically, like inverse, in fact. So you can type check this and you'll see that this is the type. Okay. So in a sense, we want to think of these functions that look a little bit like this, where you have some abstract profunctor, and it takes some PAB to a PCD in general. We want to think of those as like being like isomorphisms. Okay, and if they're like isomorphisms, then we should be able to compose them. Right? If I have A is isomorphic to B and B is isomorphic to C, then A should be isomorphic to C. And it turns out that the way we can do that is to just use regular function composition. Okay, so if I compose this swapping isomorphism, which showed that there's an isomorphism when I flip a tuple, if I compose that with itself, then I get an isomorphism that shows that something is isomorphic to itself. Right? If you flip twice, you just get no changes. But I can also compose, for example, swapping with this associating isomorphism, right? And then you get this more interesting thing. So you can you can use this as
I didn't
this
see the association isomorphism.
Oh, that's this one, yeah. That's the one where we're just moving the brackets around, where we have 3 things.
Okay.
Yeah. So this is saying I want to associate and then I want to swap. But but because isomorphisms are closed, then I get something else that's isomorphic, right? So in this isn't either an association or a swap, but they're still isomorphic, right? An A paired up with a B paired up with a C is isomorphic to a B paired up with a C paired up with an A, because I can just permute the things. Okay, so in a way, this is just a way of sort of doing type level permutations and swaps and all that kind of stuff. Anyway, so the takeaway is there's some sort of relationship between profunctors and isomorphisms, and it's sort of interesting. And we go into sort of, that's like the jumping off point, right, for the lenses stuff. Okay. So here's another profunctor. Okay. So this is a function arrow, but it's not the function arrow that we looked at before. In this case, we're fixing some return type called R, and we're just letting the argument type vary. Okay. So this, our condition was that we were negative in A, only negative occurrences of A, and that's still true, and only positive occurrences of B, and that's true because there aren't any B's. Okay. So this is a profunctor, and here's the instance, right? But because we don't have any positive occurrences, we can just ignore the B argument, what was the G argument in this case, right? So if we want to forget an A, then we can forget the B after mapping F, if you like.
What?
I don't.
Yeah.
The first place I didn't understand why B is not in the constructor.
Okay, so this is just like a function arrow, right? This is my profunctor that I'm going to build. But if this was a regular function, I'd have A and B here, and then the right-hand side would be a B. But I'm saying I'm not using B. I'm adding this type argument R, and I'm going to say that's always my result type. Okay. So I don't have to use B. The condition was that if you use B, it appears in a positive position. But I can replace it with R, and I still get a profunctor. Okay, so functions from A to R, where you're free to vary the argument A, that also forms a profunctor. Okay, and it turns out when you define lenses, this is going to be kind of useful. Okay, so this is defined in the profunctor library. I think it's in. Let's see. Forget. Okay, yeah. This is out of Edward Komet's profunctor library. Okay. So you can form something like, forget +1 or something. Find the type of that. So here my result type is any number, and I'm going to forget to take an R, and I have this sort of return type argument that I'm not using B, but I'm going to return an R, which is the same number type. Okay. But then I can sort of let's think what I want to do. So I could do something like this. Okay, so I can apply. I got that wrong, didn't I? Oh, right.
Would you mind shortening the prompt?
Oh, yeah. Sorry. 1 sec.
I think it's set prompt.
Yeah.
Oh, it is. All right. Cool. Like that? Cool. Okay, so the point is just that there's lots of examples of profunctors, okay, and this one's particularly interesting because it's going to be useful when we get to lenses and lens operations, okay. But yeah, the restrictions are very simple, right? I mean, they're very lax. Like, if you have an A, it can only be in negative position. If you have a B, it can only be in positive position. Here's some other examples. I'm just going to go through a few different examples, okay. So this is another one that is, important when you get onto the lens stuff. So we have this profunctor star f. Okay, we have this argument A, which is going to be contravariant, and this argument B, which is going to be covariant. And okay, so in general, we're going to have f is a functor. Okay, so I left this out, but functors sort of preserve polarity, right? Like positive, negative occurrences. So here B is still positive because it's wrapped in a contravariant thing. A is negative, so we have a profunctor, and you can write it like this. On the right, it's exactly the same as the function instance, except on the right you have to fmap over G because you have a functor to take care of. But this is still a valid profunctor. So we can just show an example of that. So they're all quite simple because profunctors doesn't give you many operations. But let's see. So we have the star function. It's going to construct a star for us. So let's pick some functor to use.
Why is that called a star? What is it?
So when you in the literature they write it like this. Like if you have some functor and you want to lift it into a profunctor, you just put a star on it. That, like in the literature, there's also a down star, which I'm going to show in a second.
Okay, I missed that. A star is made from a profunctor, or from a functor.
Right. Okay, so let's pick a functor and lift it up into a profunctor, right? So if so maybe is a functor or a list is a functor, so we can say just x, for example. That's definitely of type star, right? That's a star where f has been fixed to be maybe. And now I can apply die map to that, for example. So let's see if I do like +1 on the left and -1 on the right or something. Oops, keep making this mistake. Okay, so that's valid. Okay. Not very compelling examples, I'll grant you, but
I was still trying to work through the type of signature from the first one. Hit die.
no, this isn't quite right actually. Is this -1 +2? Damn it. Okay, that's right. Sorry, it's the minus, unary minus.
I have no idea what's going on right now.
Can you analyze
Okay.
this function to like something?
Yeah, you can. Okay, so if I can say unstar to drop down to the actual function, and then I can apply it to like 10 or something. Okay, not unstar, run star. Okay, so that's 13, right? So it would be, sorry, just 13. It would be just 10, but because my regular star is this, but I modified my star by before the operation I added 1, and after the operation I added 2. Okay. Or we could do something like on the way out. So like run your function in this functor and then like show it or something. Right? We get just 11. So you keep the sort of functory bit, like the maybe, but you can do this extra work at the end, or you can do the extra work. You can do additional work at the beginning. Okay. Does this make sense? Okay. Any other questions on this?
Which is applied when?
What's that? Oh, right. Yeah. So this is this is applied to the argument. This is applied to the argument. This is applied to the return value. Okay. So it's like do this, then push it into this functor structure, and then fmap this thing. Okay.
You can do the same thing with applicate, right?
Yes.
Is there any like example where only profunctor can do?
Here, let's do this one real quick. Yeah, so we'll see. So like when you do like the regular lens presentation of all this stuff, you see applicative, and that corresponds to like having multiple foci, right? Like targeting multiple parts of a bigger structure. There is sort of the equivalent of that, and we'll get to it. Yeah. Okay, just a couple more examples. So we had an f on the right. We said we can add this functor to the right hand side, which is our result type, or we can add a functor to the argument type, right? So I said that a functor preserves the polarity, so it preserves negative things. So A is also negative here, and B is still positive. So this is a profunctor, and this time we just have to do the fmap on the left. Okay. So let's write one of those. So if you have some co-star, is it with a, yeah, co-star, I think.
I hadn't worked through that slide. I wonder if you could display this
Oh, I'm
slide
sorry, yeah.
GHC.
Sure. Yeah, just ask if there's anything.
So co-star is...
So co-star is this down star thing, right? So it's like we're lifting a functor again into a profunctor in a slightly different way. We're applying it to the argument this time. So this time we can do this. We can do this additional work at the start, and then we run our function, and then we do this additional work at the end. But because our input is wrapped in a functor, now I have to do fmap over the thing first. So I do this additional work with f, but with an fmap to sort of take care of the f here, and then do my operation, and then do my final bit of work.
So you might have like a function from a list of a's to a b, like a sum or something like that.
Right. That's why. Yeah, I'm going to do a sum.
And you want to apply a function to the input from an individual element in the list to another individual element in the list is when you use this.
Yeah, so let's do a sum actually. So I want this version. Let's just do the monomorphic version. Okay, so that's a co-star where my functor is just the list functor from ints to ints. Okay. Let's call this something. Okay. And then I can look at the type of, let's say, die-map of +1 show. I think this should still work. Sorry, of co-star.
Wait, doesn't co-star need three arguments? You just gave co-star one.
Well, that's the type, right? This is the where are you looking? Sorry.
I'm looking at let co-star
here?
equal co-star sum.
This is the data constructor, right? This is co-star. So there's the type, which is co-star, which is this, takes three things, an F, a D, and a C. And then there's the constructor, which has the same name. Probably isn't helpful, but that takes a function and builds a co-star. Okay. So we had let co-star equals the co-star built out of sum, which collapses down a list and gives you a single int. Okay, and then I'm going to die map it over. The first bit of work is I'm going to add 1 to all the things in the list.
But it doesn't know where you say sum is of this type from a list of ints to a single int.
Oh, just because it's more general. Yeah.
Is it thinking about the sum function that already exists, or is that a new thing?
Yeah, so this is the sum function. I'm just specifying the type a little because it's a little bit too general. Not too general, but
So
I don't want that generality.
So you could say co-star equal co-star sum.
Yes. So I could say co-star sum, and I just get all these additional constraints that I really want. But yeah, we can work with that. So let's say I want to
make it simpler.
Okay. All right. So I called it co-star, right? So so then I can do the same die mapping operation because I have integers and integers again. I can show when I get my result, and I can add 1 on the way in, right? But I had a whole list of things on the way in. So I'm going to end up f-mapping over those, which means adding 1 to all of them, right? So the answer I should get is the sum of 1 + 1 is 2, plus 2 + 1 is 3, plus 3 + 1 is 4. So 2 + 3 + 4 is what? 5 + 4 is 9. And then show, so I should get the string representation of 9 if it worked.
Need a dollar after show.
I need to run co-star here, I think. Yeah, okay, 9, cool. All right, so again, not incredibly compelling. Like, it'll become obvious, hopefully, why this is useful. But I just want to show these examples. Okay. So another profunctor is, this is a bit more interesting, is this fold. Okay, so if I have some m, which is going to turn out to be a monoid later on, that's going to collect up some results. Okay, and I have my a and my b. Then a fold is going to be something which takes a way of sort of monoidally analyzing a b, and it'll give you back a way of monoidally analyzing an a. Okay. Everything's a bit backwards here because everything's been put on the left of at least one arrow, but if you work through it, everything is in the right position, right? So an A appears only negatively, good. And a B occurs positively because it's on the left-hand side of 2 function arrows, okay? So this one's a little weird, but it turns out it works in the end.
Wait, it's on the left-hand side of 2 because you can think of the A to M as a single thing?
Essentially, yeah. So you can parameterize this with parenthesize this with parens around here, essentially. Okay. So B occurs positively, and we're good, and it can be a profunctor, and it is. Okay. So I'm not going to show examples of this, but it is. Okay, and then one more. So there's this concept of Mealy machines, which is there's a whole library called machines which defines these things, but it's a way of sort of making a sort of function from A to B with like a notion of state. Okay, so you think of it as if you give me an A, I need to return a B, but the next time you apply an A, I might give you a different B because I have some state inside my Mealy machine. So I return, in addition to the B that I'm going to return, I also return you a fresh Mealy machine that you can run on the next input. Okay, and again, this is negative, and it's also negative in here because I mean you have to work through it. But Mealy is you have to sort of bootstrap this somehow. But this is the occurrence of Mealy AB is positive, but Mealy itself is negative in A, so it all works out. And then B again is positive and positive in Mealy, so it turns out it's a profunctor. So there's a wealth of examples, is the point. Okay, so it gets interesting.
Explain that star in there.
Oh, this is out of base, right? This is out of control arrow. So if I have two functions, I can join them together with a triple star, and it applies them separately to the arguments of a tuple. And I need to import control arrow. Okay, so I apply the left-hand thing to the left-hand thing, the right-hand thing to the right-hand thing. Okay, so.
Question.
Yep.
There doesn't seem to be, I'm looking at the library, and there's no way if you take a contravariant functor to get a profunctor, or is it just not really useful?
I think there should be a way. I don't know if there's a necessarily useful way.
There's one called clown.
Yeah. Is that in Profunctors? Yeah, I think that's the Clowns and Joker paper, I think. I've not used one. Let's put it that way. But there probably are. There's a whole bunch of examples. Okay, so this was all relatively dull so far. Sorry, because profunctors are relatively dull. But it's sort of necessary to get to this, which is the interesting bit, right? So we want to add more stuff to a profunctor. Okay, so just being able to sort of do a bit of work at the start and do a bit of extra work at the end isn't very interesting. So here's another thing we can do. We can make this subclass called strong, this class of strong profunctors. Okay, and it has these two lifting operations. So you can take this profunctor from A to B. So think about this as like a generalized arrow in a sense, because functions are a profunctor. The function arrow forms a profunctor. So we're going to use that as our sort of base intuition for these things. So we have a profunctor from A to B, and I'm going to give you back a profunctor from tuples of A's and X's to tuples of B's and X's. So you can add this information into the argument, and you can add this extra information into the return type, and you can think of it as like somehow preserving that extra information through the computation. Right? So in the function case, if you just plug in the function arrow here, it should hopefully make sense. If you have an A to a B, then you can get an A and an X to a B and an X, because you just apply, well, it's this, right? So type, if I take my F, it's the function I just showed, right? The type names are a bit rubbish, but if I have a B to a C, which is my PBC, then I want a P BX CX, and it's decided to pick C prime for this thing. But this is a valid implementation of first, right? So again, just like for profunctor, function arrow is a strong profunctor as well. So we can do these slightly more interesting things. Okay. Yeah, and it turns out all of the examples that we had before are also strong profunctors. Yeah, sure.
Where's the X coming from?
Oh, this is there's a for all here. Sorry. Yeah, so for any X you choose, I can lift up your PAB into a P where I've tupled with X on both sides. Okay.
So I would have thought you could always do that.
Not in general.
Just apply the thing to the first argument.
It's sort of tricky to find a counterexample, but there are counterexamples. Oh, yeah. I did like a counterexamples blog post at one point for all of these classes so I could like understand them. And it took me, this was one where it just took me ages to find one. So it's, yeah, it's.
There are profunctors that are built not using the template that he's been using. You know, he's using this template of like applying something on one side, applying something on the other side. Right. And that gets you a profunctor, but there are other different profunctors out there.
Yeah, exactly.
Really?
Everything built out of functioner, that's the only way to get something negative division.
So where do you get counterexample?
I can find one and post it on the meetup comments, but I can't remember it off the top of my head. Well, actually, maybe I can give you one from here, right? Come to think of it. So let's see. Here you go. Right. So CoStar. This is going to be very opaque, and I'm not going to be able to motivate it very well. But CoStar was a profunctor for any functor, but you need it to be a comonad for it to be strong. So if you have something that's a functor but not a comonad, then you can't make CoStar into a strong profunctor, but it's still a profunctor. So I'm just going to leave that, and it's going to not mean much, but there it is. So all of these things can be made into strong profunctors in some way. So we had this thing forget where we were just fixing the right-hand side. That's automatically strong. It doesn't matter what R is. Star is still strong for any functor. I just said CoStar is strong, but you have to strengthen the functor you're interested in to a comonad, and fold and melee are both strong. Okay. So we can think of this as just, we have some sort of abstract notion of function arrow, and it has some way of lifting up tuples, right? We can like preserve this information through our computation. Okay, so the motivation for all of this originally was that we had these isomorphisms and that you could compose them. So let's just look at first and second, right? So let's go back a second. First and second were these two things that lifted up our operations, right? So we had PAB, we can extend on the right with an X, just stick this extra bit of X that you want to preserve in the right-hand tuple argument, and then the second where X goes on the left, okay? So let's look at the types. I think it's actually first prime. Yeah, okay. So this is the type of first prime, this is the type of second prime. Okay. So we could compose things, when we looked at isomorphisms, we said that we wanted things like this to be isomorph. We wanted to think of these as like being a bit like isomorphisms, right? And we could compose them. Well, we should be able to compose these two, right? Because they're both of the same sort of shape, right? We have something that takes a P to a P and something that takes a P to a P, and as long as this thing unifies with this thing, which it can if you pick A and B suitably, then these things should compose, right? So we can say, give me the type of first and then second. Okay. So this is like saying, if you give me a P from an A to a B, then I can give you a P from this triple where A is like embedded in the middle, and I'll give you back another triple where I've swapped it out for a B. Okay. So I can go like deep inside these tuples and apply this function, and then come back out and put in the bits of information that I had while on the way in, right? So it's sounding a lot like lens, right? So we can form all these things, right? So we can say first takes my PAB and it goes inside the first argument and applies this function, and then it comes back out and gives you back the X you had in mind. First goes into the first argument, and then it goes into the first argument again. So we have a triple and we go left, left. And then I keep the X and the Y that you had in mind, put them back in on the way out after applying the function. And then first, second goes into the first argument and then the second argument of that tuple, right? So the A is on the right-hand side of the left-hand argument. Okay. Is this making sense?
So this is kind of opposite of how you normally think of how function application is, right? The composition.
Yeah, so the composition is a bit weird because you have you have to, like lenses, right? You have to sort of think of them this way. But it just works out that way because of the way the arrow goes here, like PAB to the bigger thing. Yeah, okay. So they compose just like the isomorphisms composed, right? So they're starting to look a lot like lenses. The cool thing is they also compose, these two classes of things also compose with each other, right? So everything that's strong is also a profunctor, because it was a superclass. There was a superclass relationship between strong and profunctor. Okay. So that means that if you have something which can lift something over a profunctor, then you can automatically lift it over a strong profunctor, because every strong profunctor is a profunctor. So in other words, every isomorphism is also an example of a lens. Okay. So a sock was one of our examples of, I think I only defined swapping in here. Let's just check. Or maybe I didn't. Okay. Well, we'll just do swapping. It's a little easier. So we can say, oh, because I reloaded. That's right. Import data.tuple. Tuple. I can say let swapping equals dymap swap swap. Okay. So this is one of our proposed isomorphisms, right? So it takes a function from a B to an A to a different A to A and a B, and it swaps everything around before and after applying the function. So it gives you a function from ABs to BAs. Okay, but I can compose this with first. Right? So I can say swapping composed with first, and that gives me this thing. So this says if you have a function from B to an A1, these type names are terrible, then you can give me a function where you apply that on the right hand side of this, right? Something seems a little off here. I think maybe I got this the wrong way around. Type first. Okay, that seems better. Okay, so I can take my function, apply it in the first component, and then swap everything after that. Okay, so this one's a little complicated because everything's tuples, but we'll get to examples where there's sort of more standard data structures. But the point is you can compose isos with isos, and you can compose lenses with lenses, and lenses with isos. So we're sort of building up, just like we have in the lens library, we're building up these different classes of operations on data structures, and we're trying to do it in a way that everything stays composable with everything else. Okay. Okay. So at this point I was just going to give a quick overview of lens for anyone who's not seen it, just in GHCI. Who's not seen the sort of basic lens overview on some video? Okay, cool. We'll just go through it then. So if I import control lens, that should give me like all the interesting stuff I need. So lenses are used to identify small bits of data structures inside bigger data structures. Okay, in such a way that I can do things like, given the bigger data structure, I can ask for the value of the smaller data structure, or I can take a function that acts on the smaller data structure and lift it up to act on the bigger data structure. So let's see some examples of lenses first of all. So we can, so two typical lenses are these. Oh, right. This is the downside of the lens library, is that the types get pretty horrible. Well, ignore the types. We're just gonna look at some examples. All right. So, so if I want to look at the value of a smaller data structure inside a bigger data structure, I can use the view function. Okay. So maybe this type should be understandable. Okay. So getting is like some type of lens. Okay. So we can think of this as pulling out. It's a lens type thing that pulls out an A inside of a bigger S data structure. Oh man. Sorry. Bear with me. Do this. Okay, I gave up trying to understand these types a while ago. So, okay, so if I want to take this bigger data structure, this tuple, and I just want to look at what's in the left-hand side, then I can use the view function and pass in a lens that identifies that small bit as appearing somewhere in this bigger structure. So that's not very interesting, right? Because I could have just said, first. But the interesting thing is that we can compose these in the same way that we had a second ago, right? So I can say, go inside the first component and then go inside the second component. And that'll pull out the true, right? So these are like functional versions of like object accessors, right? Or getter setter pairs or something in imperative language, or object-oriented language, I suppose. But in the but with the nice property that you can compose these things, right? So you can define all these atomic getters and setters. That you can bundle up these getter setter pairs for all your sort of basic types, and then you can compose them to talk about data structures that appear in very sort of nested locations in very big data structures, and then go and modify the values and get values and do all of these nice operations. Okay. So another example would be something like, let's say I want to switch that true for a false. Okay, so this is some data structure that I have. Got to remember to get these the right way around. Okay, cool. So I give the lens, and then I give a function that I want to apply deep in the structure. And then I give the big structure, and it's going to give me another big structure with the function applied to that little piece. Okay. And I mean, I'm not going to go into all of the functions in the lens library because there's way too many. But there's a lot, and you can do a lot of really interesting stuff. But you can also do things like, let's see. So I can say, look at the first element of, well, let's just do just for now. Okay. So I want to see what's inside the just constructor of just 42. Let's see. I think I need preview. Okay, sorry.
What is underscore just?
So I'll tell you in a second. Sorry, just one second. I'm going to pick right actually. Okay, so underscore right is what we call a prism. So it's an idea like a lens, but instead of picking out a structure deeply inside another structure, it picks out a structure which may or may not be there. Okay, like a constructor for a sum type, like either, right? So either can be a left or a right, and I can say, is this a right? If so, pull out the thing that's inside the right, and that was 42. And it succeeded, so it marks the success with a just. Okay, so it says just 42. But I can also say, pull out the thing from the right out of left A, and it says nothing. There's no right. You gave me a left. Okay. I should be able to say something like this. Okay. So now I'm saying go inside the first element of the tuple, see if it's a right, and if it is, give me what's inside. Well, it wasn't a right. But if it was a right, then it can pull out the A. Okay. So this was a lens and this was a prism, and I can compose them together. So we have these nice compositional properties, right, where we have these families of different optics in general, we call them, and they all compose in nice ways. So you can use all of these functions like view and over and preview, all these things. Right, so I think we can even use over on this.
So are these underscore right and so on derived automatically from right, so to speak?
They can be. So there's template Haskell machinery that will derive this for you in the lens library. These ones in particular, though, are actually just defined in the lens library as like sort of standard lenses and prisms and stuff. That just come sort of baked in. So I can also apply, the set of functions is fairly rich that I can use. Where I can apply over. That was the function that sort of given a function that acts on the small piece, lifts it up to a function that acts on the big piece. Okay. So say go inside the left-hand side of a tuple, see if it's a right. If it's a right, apply the odd function, which pulls out the ordinal value of a character, which is 97 for A. If I gave you something which was not right, then it just doesn't apply it, right? I get left 42. So there's one more, so I can say something like traverse. Go right here, and now I have 42, 1, 2, 3, 0, or something. Oh, that is not a chart. Oh, well, let's do A to Z. Okay. So we have a lens, we have a prism, and we have a traversal, right? So a lens was something which picked out a small part of a bigger data structure that was always going to be there. A prism picked out a part of a data structure that may or may not have been there. And a traversal picks out many parts of a data structure that can be there. So you have 0 or more focus points in this case, right? So here I'm saying I have a tuple. Inside I'm going to have an either, and inside I'm going to have some traversable structure, which in this case is a list. Okay. So go inside the left-hand side, see if it's a right. If it is, traverse over the array, and at every focus point, apply the odd function. So now I end up with this data structure that has all these ordinal values in it. Okay. But if it was a left, then, whoops, right. Tuple. Oh man, either something or let's say it's an int. Did you give me an answer? No. Oh, well, type inference problem, but.
Because it's making an error at compile time, is that what it is?
I think it's just because it has a type variable that it can't solve. Let's see, so if I say that's going to be an either a list of integers or let's say a string, it doesn't really matter, or an integer in with char. Oh, of course, no. All right, I'm not sure. There's some type error here, like because of the sort of ambiguous type variable, but
right and the or.
Yeah, because I said it was left, and I asked for a right. The sort of either here could have any type on the right, So it's struggling to figure out what that is, but oh no, I see. It can't figure out what the traversable thing is, right? So that's why. Well, anyway, if I gave a type signature to the right thing, it would figure this thing out, right? But sorry, this is. Let's see if I can figure this out real quick. Either. So what was that? A string or an int. An int. Whatever. Never mind. Yeah, we'll leave this alone for now. All right. So the point is, Lens defines this sort of rich family of functions that you can use on all these different types of focusing operations, and all the focusing operations compose with each other really nicely. So the goal of the Profunctor lenses stuff is going to be to reproduce that in a lightweight way with the Profunctor machinery. How am I doing for time? Because I can carry this on another time. All right, cool. Okay, so before we said that we wanted to think of
a library.
No, not that I know of. There might be one, but I haven't seen it. But there's one in PureScript that we worked on. But yeah, the Profunctor approach, I don't know of any Haskell library that implements it. So I said that we wanted to think of these sort of actions that act on this abstract profunctor and take one profunctor arrow to another profunctor arrow as being something like isomorphisms, right? So we had things like die-map, we had swapping, and we had a sock. And we wanted to think of those as isomorphisms. So in the same way, if we strengthen the constraint to strong, now we want to think of these things. Oh, thanks very much. Now we want to think of these things as being like lenses, right? So we saw some examples, and we saw that first was a lot like a lens, and second was a lot like a lens, and we could compose them and get first or second, and that was a lot like a lens too. Okay, so this seems like it should provide a decent basis for talking about lenses. Okay. So now, this is a bit of an intermission, I guess. I want to talk about this sort of different way of thinking about lenses, which doesn't come up very often, as far as I'm aware. But if you look at the type of lens, so a lens, so we give this type signature with these 4 type arguments, right? So we have the big data structure is S, and the little data structure that's inside it is an A. And if I turn A into a B, then I end up turning the big S into a different big T, right? So it might turn out that S and T are the same, and A and B are the same. And for most cases, that's probably going to be the case. But they don't have to, you know, we can do these sort of type changing operations, right? So we had, where's my working example? So if we look at this, right, now the type of this in here was a string, right, a list of characters, but on the way out it was a list of integers. Okay, so I have these traversals and lenses and prisms in general can act as like type changing operations, not just fixing the type, right? So we have, that's why we have these 4 arguments. Okay, so a lens can turn an A into a B on the smaller data structure, and in doing so turns an S into a T, the big data structure. And the way we define that is for all P. Yep.
S and T, are those what do you call it? Are those of kind star to star?
No. Well, we want to think of it that way, right? So we want to think of these as being like somehow the same, and in general they'll be. They might not be kind star to star, right? This wasn't kind star to star because, but you know, in general you probably want to like be able to wrap it up in a new type or something, and like,
so that's not,
and then it would have that kind.
In that example, S and T aren't the list monad?
They can be, but they could be like monomorphic things, right? So it could be something like S and T could be like byte string, and A and B could be text or something. It could just be like the isomorphism that shows that byte string and text can be encoded and decoded or something. So they're not in general going to be polymorphic containers, but they can be. But we want to think of, like the intuition is good, right? We want to think of S and T as being somehow the same, and a good way of thinking about that is like they should, if they vary, they should vary by some type argument. Yeah. Okay, so
that's not the same as the usual definition of lens. Is that bigger?
It's not, right? So this is a profunctor lens. So if you look at the type of a regular lens, right? So this is where star comes into play, right? So so a regular lens looks like this for some functor, right? That's Van Laarhoven lens, right? Well, that looks a lot like this definition if you pick P to be star, right? So star was A to FB, and then I have S to FT on the right-hand side. Okay, so every profunctor lens can be turned into a Van Laarhoven lens by choosing P to be star, but you can't, or maybe you can go the other way, but I'm not sure. I've not seen it if you can. But certainly every lens you can encode this way, you can encode, every lens of this type can be turned into a Van Laarhoven lens, which is this one. Okay, but anyway, so if we look at the type, right, this is our sort of like candidate type for what a lens should be. So how can we actually inhabit this type? Right? How can we pick something that has this type? So I can't use any information about P because I have to be able to do this operation for every P, right? P is completely abstract, but I know that P is strong. Okay, so if you're given a PAB, you need to be able to turn it into a PST. All right, so one thing I might be able to do is use the tupling operation like first from the strong profunctor class and turn this into a P from an A and an X to a B and an X. Okay, and then another thing I might be able to do is try and find an isomorphism between A and X and S, and then apply that, and that would allow me to turn this into a PST.
What's
okay.
X?
Oh, X. So when we looked at the type of first, here, right? This is the type of first. So it said you can pick any X, and you can lift up a PAB into a PAXBX. Okay. So I'm saying one way we might be able to come up with one of these things is to find for one of these lenses is to find an X such that A is isomorphic to S is isomorphic to A and X, the tuple.
Find an S.
Find an X such that S is isomorphic to a tuple of an A and an X, because I can use first to lift this up to a P AX BX, and then I can apply my isomorphism to turn it into a PST if there's the isomorphism there. Right? So in a way you can think of a lens as saying your big data structure is isomorphic to a tuple of the smaller data structure and some other stuff. Okay.
No matter how far you're reaching into it, you can still think of it as a tuple.
Right. So concretely, right? If you have this like normal form of a lens, if you like, where if you have this isomorphism, this like type changing isomorphism, if you like, where you can take an S and get back a pair of an A and an X, and then you can change the A into a B, and then you can go the other way in your isomorphism and take your B and your X and get back a T. Right? So we change the A into a B, and the S gets changed into a T in the process. Right? Then we can construct a lens, and all we have to do is lift up PAB with first, so that was picking your X and sort of forming this PAX BX, and then using this isomorphism that you have with this pair of functions to turn that into a PST. Right? So this is one way to make a lens, but the point of this slide is to say you should also have in the back of your mind that lenses somehow are identifying big data structures as small data structures tupled up with some other type X, right? So they're hiding some type X that can be tupled up to give you the big data structure. Does this make sense? Any questions?
On the normal form, am I reading that type? And then I'm just counting the number of arguments
This one?
to the type. Isn't there something missing?
Here?
The last one, in it.
Oh.
So you have 3 arguments.
Oh, right, because a lens is also a function, right? A lens is a function from PAB.
Right.
Right, so we have a PAB here as well.
Yeah.
Yeah, so the point is, if you can identify S and T as being sort of uniformly equivalent, uniformly isomorphic to this tupling with X, so, you know, A is to S as like B is to T, if you like, with this tupling operation, then we can form a lens. So the lens somehow like identifies big data structures as looking like tuples, where one of the sides of the tuple is the small data structure you're interested in. Okay, so if we pick a lens, so one lens that we had was first, right? And first had the type. First was a lens from a tuple to the type that was in its first argument, right? So we're saying that lens identifies the tuple as a tuple of its left-hand side with some other thing. And of course it is, right? Because it's a tuple by definition. You can just pick the right-hand side of the tuple to satisfy that. But what about like first.second? So first.second identified identified an A identified an A inside a triple of an A and a B and a C, okay? And we're saying that that's got to be isomorphic to some tuple with A. And we can pick B and C, right? So let's write it out. First.second is a lens, okay? So here's the type, okay? So if what I'm saying is true, then that means that this lens should in some sense identify A as being isomorphic to a tuple, it should identify this as being isomorphic to a tuple of A with something. And I'm saying we can pick that to be the other thing, okay? So in general, there's some type which might not be obvious, but you can choose it, that tuples up with A to form the bigger structure that the lens is working over. So that's just another sort of way of thinking about lenses, okay? So in other words, if you have some isomorphism between S and some tuple with A in it and some X, then you can turn that into a lens, okay? And the way you do it is to use first. So you lift up your arrow with first, turn it into this arrow on tuples, and then you use your isomorphism to turn it into the final arrow that you want. And you can actually go the other way, but it's a little bit of a pain. So you can write this function with a bit of work that says, if I have a lens that identifies an A inside an S, then there exists some X that's abstract for which S is isomorphic to a tuple of A and something else, that X. Okay, so here's some lens combinators I think I showed get and modify earlier. Set can just be implemented using get, using modify. But we can implement these using our profunctor machinery, right? So our lens type was some operation on strong profunctors. So in order to do anything with with one of these lenses, we have to pick some strong profunctor to operate on. Okay. So I'm saying that if we pick our strong profunctor to be forget, then that's enough to define this get operation. Okay. So let's work through this. So we have the type of forget identity is this, forget RB. Okay, so we're fixing some return type R, and we get an R as input, and we have B as this output argument that we're not using. Okay, and then let's pick a lens. Okay, so let's pick our first lens. Okay, so forget was a profunctor, so first is going to lift it up over A and B. So it's going to take, now it's going to take an R, and this would have been Rx, but let's call it C, from an R and a C to a B and a C. But remember, R was not one of our profunctor arguments, so that stays the same. Okay, now we can say run forget.
What stays the same?
R stays the same, the first argument, because that wasn't one of our A's and B's.
R is the same in what and what?
Here, right? So we had forget R and B, and now it's become forget R, so that one didn't change, but this one had become an R and a C. So on the second two we tuple up, right? Because this was a profunctor in the second, the last two arguments. Okay.
Anyway. I'm not following. I'm probably just forgetting the definition of something. Can you walk through that again?
Yeah, we can go back to forget as well. Yeah. Oh, actually, we can just show it in here. That one. So this was forget, right? Here. So this was the one where we said it's like a function, but we're going to ignore the B, and we're just going to fix some constant return type. And we're going to contravariantly map over the argument, but just forget about the result. Okay. So this is a profunctor, but you have to, right, so for this to sort of kind check, you have to pick an R, right? It can only, like, it's a profunctor in A and B. So I pick some R, and then forget R is a profunctor. Okay. There. Right. So then, because a lens can act like this on any strong profunctor, I can pick P to be forget. Okay, so if I just substitute forget in here, that says that a lens can act like forget AB to forget ST. Sorry, forget R AB to forget R ST. Okay. So we can pick the identity function that gives us a forget R RC, whatever it was. Then we can act on that with our lens, and that gives us this.
Wait, forget identity. What is that?
So that's constructing one of these forget functions. Right. So here's the forget constructor. I need to provide some function. So I'm going to just pick the identity function. Turns out this is just what you need to make this work, to get the view function, the get function, right? So that's going to identify A and R, right?
Wait, but if you say it's identity, or you're saying that A to R function is the identity, then haven't you specified what R is? I thought you had to leave R general.
So no, I can pick any R and I get a profunctor. So in this case I'm picking R to be the same as A. Okay. So forget at the identity is going to be a forget of A and then B, because A and the R and A turned out to be the same thing. They're both going to be A. Okay. So then I can map that over my profunctor, and I'll get forget A ST over my lens. Sorry, you get forget A ST, and then you can pull off this forget constructor, and you'll have another function inside. And in that case, you'll have, what was it, an S to an A, and that's exactly what you need for a get. Okay, so it's here, right? So if we pick the first lens, okay, and we just plug this in, then we get the type of get. No, here we are. We get the type of get for the first lens, right? So we It's the thing that pulls out the first argument. If you put it in like first dot second, you get the type of the getter for this R inside this triple. Okay. And if you pick, well, yeah, I mean, it's the same, right? If we do like first again or something, then it's going to put the R here. So that's how you can define a get operation for a lens. Okay, so I can write this function. Okay, I'm going to skip set because you can just implement it in terms of modify. But how can you define modify? So modify says, I have a lens that identifies an A inside an S, and I want to turn an A into a B, and in doing so, turn this bigger S into a T. Okay. Well, again, so in order to use a lens, we have to pick some strong profunctor. And in this case, we can just pick the function arrow. Okay, so the function arrow was a strong profunctor. So we have a function from A to B that's of the right type that we can just apply the lens to it. Okay. So if we go back a second here, right? So now if we just pick P to be the function arrow, so this will be A to B, this will be S to T. That's exactly the type of modify, right? So that one's much easier actually. So in order to implement modify, we just apply the lens to the function you want to apply inside the structure, right? So let's say we want to apply first dot second, get the type of this applied to show or something. Okay. So this is going to take a showable A, and it's going to be inside the second component of the first component, and I'm going to show it and turn it into a string. So I can say something like oops. Okay, so I'm showing the true here. Right? So that's how you define a modify operation. So you can build up lots and lots of like lens type operations just by making some sort of cunning choice of a profunctor to slot in to the type of a lens, and then you just apply it like a regular function, right? And you might have to do some new type unwrapping and wrapping, but generally it's pretty lightweight, and you can define a whole bunch of functions this way. And the reason this is useful, by the way, at the start I said there's an awful lot of profunctors, and there's also an awful lot of strong profunctors. So that means that if you can manage to write a lens, then you have an awful lot of data structures that you can apply it to. Okay, if you can think of any strong profunctor, like say there's an awful lot of them, then that gives you an automatic lifting operation for any lens. Okay, so that's why I think that profunctors and strong profunctors and all these different types of abstractions are like sort of undersold. I mean, everyone's sort of familiar with like applicative and monad and these types of things in the Haskell community, but like people don't sort of give these as much credence, but they give you an awful lot of lifting operations, right? So if you have any lens, that means you can lift, you can form a lifting operation over any strong profunctor, of which there's a lot. So it's a good tool to have in the toolbox. It means, it might be hard to write a lens, but if you can write a strong profunctor, then you get a lot of freebies in terms of functions you can write. Okay. All right. Any questions on that? I should probably wrap up soon, right? What time are we on? 9 o'clock, nearly.
We're not in rushing.
Okay. Well, I can keep going. I've a fair amount of stuff, but we can break it up. I don't mind. Okay. Any questions on this stuff? First of all.
I do. So, did you find anything? Like, what did you find doing this with profunctors that differentiated it from the way Comet did it?
In the lens library?
Yeah.
Yeah. So I have a slide about that at the end actually, but so there's a couple of things. So one thing I like is that the presentation is like really uniform, right? When you get onto prisms and traversals, it like generalizes really cleanly. And if you look at the lens approach in the lens library, the types are a lot more complex. So you have like, choice and profunctor, but you also have things like applicative and contravariant, and they're all like mixed into the types in the lens library. So I like the type presentation of this a bit more.
Did Matt tell you why he gave up on these for Haskell?
Yeah, so there's pros and cons. So I'll get onto it at the end actually, but yeah, my main reason is that the type presentation is cleaner, I think. So, but I'll talk about it a bit more at the end. Okay. So we have these strong profunctors, and I said that they identify big types as looking like tuples of the small type you're interested in with something else. Okay. Well, there's a sort of like entirely dual presentation where instead of looking at tuples, we look at sums. Okay. So we just switch all the tuples for sums, and that gives us this type class called choice. Okay. So strong and choice are related, just like the tuple and either are related here, if you like, right? So in this case, so I said a strong profunctor lens identifies a big structure as looking like a tuple. Then this choice optic will end up identifying a big structure as looking like either the small structure or something else. Okay. And all the sort of motivation for like how we form that intuition about, you know, the normal forms and the isomorphisms and all that kind of stuff goes through exactly the same. Okay, but we have a name for that, right? That's a prism. That was what we looked at earlier. That was like the left and right prisms that we had.
Sorry, prism is a name for what?
Prism is this thing that we had before, right? So we had preview. When I did preview, and we had like left 42 or something. And like right. Okay, so that was a prism, and this is the lens library, right? This is a regular prism from the actual lens library, but we can produce something that acts just like a lens by using this choice class, just like we used the strong class. Okay, so it's exactly the same. Okay, and we have lots of examples again. So this thing is like a nice rich abstraction because there's lots of things we can apply it to. Forget is choice, so we get something a little bit like the get operation, but it only has choice when the return type you're interested in is a monoid, right? Because you have to have some empty value for when the thing doesn't match. If I said give me the thing inside the right and I gave you a left, then I have to have something equivalent to the nothing that we had, right? And that's going to be my m empty from the monoid. Okay. So this is slightly weakened. I have to have this monoid constraint, but you still get choice for forget if you have a monoid. And again, I said star was like the way to sort of like get the Van Laarhoven presentation from this, and in the Van Laarhoven presentation, if you want a prism, you need to have applicative on the functor. Well, if you have applicative, then you get choice for the star profunctor. Okay. If you have a comonad, then co-star is also choice, and then fold and mealy are also have choice, right? So for example, like fold was this thing that said if I can interpret the result type in some monoid, then I can interpret the argument type in some monoid, right? Well, if my lifting operation.
Could you show the definition of choice again?
Yep. So it's this one, right? So I have left and right. So just like I could lift up A and B before to a tuple of A and X, now I can lift it up where I either have an A or an X, and you can get back either a B or an X. And again, I guess I missed this, sorry, but the function arrow also has choice, right? So so that's important when you want to define modify for prisms, right? When we use the function arrow there. So if you think about what would happen if you substitute the arrow for P here, right? So you have, if you give me a function from A to B, then I can give you a function from either A and either an A or an X to an either a B or an X. Well, sure, right? If you gave me a left A, then I can give you a left B where I just applied the function you gave me. And if you give me a right X, then I'll just give you the X back. Okay.
So, I don't know how to phrase this question correctly, but so
sure.
Strong and choice, they're very similar constructions. You're sort of like passing choice or strong as some kind of higher order.
Yeah, well, so they're really close, right? Like one just picks tuple here and one picks either, but you could pick something else, right? You could
parameterize that?
I think so, yeah. I mean, well, it's difficult to, well, you might end up with some like gnarly functional dependency issues or something, right? Because you have to have this the choice instance depend also on the type constructor you want to parameterize with, but you could give it some, you could give it some type constructor or something like either or tuple, and maybe come up with some generalized thing. I haven't seen that done, but I mean, you probably could do it, and you probably could apply this to other things, right? Like you could apply it to like the XOR type constructor or something, where you can have like one or the other or both, and you'd get something a bit weird, but it'd be like a valid optic, I think. How many instances you'd have for that thing, I don't know, but there'd be some like stuff there.
Philip,
yeah.
on that choice mealy, has anyone done anything with choice more?
I'm not sure if more is a. It almost certainly is like some of these things. I don't know if it's. Yeah, I'm not sure. I'll have to have a look. It's in the machines library though, I think. So, I mean, Edward Commit sort of like defines instances very like gratuitously. So if it is an instance, I'm certain machines will define the instance. Yeah, somewhere it will be defined. Yeah, so we have like lifting operations, just like we had lifting operations for lenses. We can lift up things over prisms, right? And like all of these profunctors benefit from this stuff. Okay, so left is a prism. Okay, that's just another name for this underscore capital L left thing that we had. Okay, so it chooses an A in the left hand side of an either A or X, and left composed left is also a prism, and it identifies an A inside the left, left component of the left component, and then you can compose like left and right. Okay, but again, they all compose with each other, right? So you have all these families of things, and they all compose. So you can say, look inside the first element of a tuple, and then check whether it's a left-hand side of an either. So that's identifying this A inside this either inside this tuple. Okay, and you can also compose them with isomorphisms and stuff, right? So you could stick like a swapping or an a sock or whatever in there, and it would work too. Okay. Yeah. So I already said this, right? But the strong stuff gave us lenses, and choice gives us something that looks a lot like prism. So by just swapping strong for choice, like swapping that tuple for an either, we've like rediscovered prisms, if you like.
Can you remind me, is there a brief description of what the difference is between a strong and a choice? Right.
So strong. So it's all a bit abstract. I mean, I think of these. It's all a bit like. Strong and choice are quite abstract. I think of them as things that can be lifted over lenses and prisms, right? Like, so it's all a bit like backwards, but
I don't know what prism is.
Yeah, prism was like that left. These are all prisms, right? These things that identify data constructors, if you like, are like bits of a sum.
I think he's asking a lens library is prism.
Okay.
Is that what you were asking?
Is what was it?
I thought you were asking definition of the prism in the lens library.
I don't know where it's defined, but I just want to know what it is.
So lens was this thing, right? Like this one. This is prism. Sorry, prism. This is prism defined in the lens library, right? You can give me some data structure and something that I want to try and match, but it can fail.
Like that? Every prism is defined by a type constructor?
No, right? So here's one. Here's one.
Okay, but at bottom are they all?
What is the type?
Not necessarily. It's going to be pretty gnarly, I think. Let's see. Yeah. So this is what I mean when I say the type presentation is a bit nicer, I think, in the profunctor way. So yeah, it's pretty hairy. Like if you have some choice profunctor P from A to FB, yeah, and applicative. Yeah, I think the profunctor presentation is nicer, right? Because if you look, this is our equivalent. Now I just have like one constraint, and it's all very uniform, right? I take my P to a P.
So are they all based on maybe all the prisms?
No, this one. Well, this is based on either, right? So the return value here is just, but that's just because the type of preview returns a maybe, I think. Yeah. So preview is returning a maybe because it's like saying try and find this bit of data inside this piece of the bigger data structure that may or may not be there. And if it's not there, you're going to be able to give me back in nothing. Okay.
Okay, so the present doesn't tell you what to do in the case that you don't find that thing.
It can. So it depends on the operation you're trying to do, right? If you're just doing a preview, it's either there or it's not. But in general, yeah, there's operations where the prism can sort of like say what to do in the case of failure and things. But I'm not going to get into those. I haven't even used them, but they're there. Yeah. Okay. So anyway, so this table is growing, right? We had profunctor, and that motivated strong, and then we dualized it. We got prism from choice, and just like we said before, every strong was a profunctor, so that meant that every ISO was a lens. Similarly, every choice is a profunctor because we have the same superclass relationship. So every ISO is also a prism. I got that the wrong way around. Every prism is also, every ISO is also a prism. I'm sorry. That's right. Every ISO is both a lens and a prism. But it's not the case that a lens is a prism or a prism is a lens, right? They're sort of like different branches of the tree because there's not necessarily any relationship between strong and choice in general. Okay. So they're not related in general, but you can compose them and you get something. Okay. Well, what do you get? So let's say you pick first and left, and that's going to pick out an A inside this tuple of an either, where A is in the left-hand side of the either, right? Well, that's not a lens and it's not quite a prism, but it's an optic of some sort, and we call it an affine traversal or a 0-1 traversal, right? So a 0-1 traversal is like an optic where you can have exactly 0 or 1 occurrences of the thing, right? So in here, you either have an A or you don't, but you can't have more than one A. But the crucial difference between this and a prism is that with a prism, because you're identifying the thing as a sum, you can always turn a prism around and reconstruct the bigger thing. Okay, so with left, I can say, is this a left? But I can also say, given the smaller thing, give me back the bigger thing, because I can just apply left as a data constructor. But in a 0-1 traversal, I can't do that, right? Given an A, I can't construct one of these things in general because I don't have a Y sitting right. If it were just either, I'd be able to just apply left. Okay, does that make sense? So this one's a little weird. You can do plenty of things with it, but it's not a lens and it's not quite a prism. But the point is that these classes of things are still closed. Just you have to sort of enlarge the thing you're looking at a little bit. Okay, so just like we had this normal form idea for lenses, where we could say that a lens was basically an isomorphism between a big thing and a tuple. Now we can say that a prism identifies a big data structure as a sum of a smaller thing and an X. Okay, and this is basically the exact same implementation, except I swapped first for left here. Okay. So I've just written that a prism asserts that the family of types given by S and T is uniformly isomorphic to a sum, where one of the sides is the A or the B. Okay.
Those words sound like they might make sense, but I don't have time to go through.
Okay.
So every prism is like this?
Yes. So every prism identifies some big structure as looking like a sum where one of the summands is the small structure. Okay, so left identifies either AB as a sum because it is a sum, right, trivially, and one of the sides is A.
Wait, maybe I don't understand what is a sum?
Like either is a sum type. Right.
Any pairing of two other types. So a pair A comma B is also a sum, but either AB is a sum. So any kind of thing like that is called a sum type.
I don't know what you mean by a thing like that.
Well, anything that is, so if you make a like data thing AB, then that's a sum. So right, data capital T thing AB, then that would just be that's an example of a sum type.
So here's one, right? So here's a sum type, right? Ordering from Prelude is either less than or equal to or greater than. Okay, so it's a sum. We say it's a sum of these three things. It's one of the three things.
I'm wrong. Right, I'm wrong.
No,
Yeah.
I thought you were right, but okay. Okay, so you could define prisms for each of these things, right? You could define a prism for less than.
Is or the idea?
That's right, that's correct.
Yeah.
It's or.
Okay.
So just like for a tuple and strong and lens, we have, I have both of these things, I have both of these pieces of data. That's a tuple. So a sum is I have one of these many things. Exactly one of these things. Yeah. So a prism is picking out, like, is trying to pick out one of these summands. Okay. We're almost at the end. Okay. So.
Wait. So I didn't understand that page. So,
oh no.
They're normally easier.
Yeah, I feel a little bad. Sorry.
This is what I wanted from you. I knew what I was getting. Okay, so now I understand that a prism is a sum, or I believe you that a prism is a sum. But does this show why?
So when we got to lenses, I said I wanted to give you this alternative way of thinking about it. Like a lens identifies things as tuples, big structures as tuples with smaller structures. And I'm saying that a prism tries to identify a big structure as like either the small structure or something else, right? So in this case, like I could give you a prism for less than, and I'm saying that is a little bit like saying less than, like ordering is like less than, either less than or this other thing, right? If I push these into their own little data type, then I could give you an isomorphism between either LT and the other thing and ordering, right? And that's what the prism is doing. And you can sort of make that concrete, right, by saying if you give me an ISO between S and either AX, then I'll give you a prism back that identifies that. Okay. Okay, we're almost at the end. I'm going to skip arrows. I'm going to skip that too. All right. So we did profunctor and we got ISO, we did strong and we got lens, and we did choice and we got prism. But you can do lots of other things, right? So if you can pick any old constraint you want on P, and you'll get some optic. Whether it makes sense or not, that's another question, but there's plenty of things for which it does make sense. So there's this class called traversing, okay? So it has strong and choice as superclasses. And it says, so this in some sense like generalizes both left and first, right? So I want to skip over this pretty quickly, but either in tuple, so you asked how we can generalize and like parameterize over either in tuple. Well, this is one example of a way to do that, right? So you could say either and tuple are both traversable structures. So I can unify those two types of first and left by doing this, right? I can say you have to given a PAB, you have to be able to lift this over any traversable container. So that might be tuple, it might be either, it could be anything, it could be list, right? So traversing, when we form this optic with traversing, we get something that looks a lot like traversal from lens, okay? Because I could pick like T to be list, and now I'm traversing over the elements of a list, right? I'm saying lift up this operation over all of the elements of the list. Okay, I think this is actually in Comet's library. No, okay. Question?
Just to get my head straight, so we were talking about the choice, which is strong with respect to either, which is a sum type.
Mm-hmm.
But when we're working with lenses, we were working with tuples, which is a product type. Or is it also
lenses was a product type, yeah.
So that means that tuples is a product type.
Yes.
And traversal generalizes both of them, saying that, so traversal could specialize to lens or prism depending on it.
Yeah, so you want traversals to generalize lenses and prisms, right? Because if I have, so a lens is like saying I have one smaller structure inside this big structure, and a prism is like saying I have one summand, or like one bit that might be there, so that's like 0 or 1 if you like. So in both of those cases I should be able to traverse over all the foci, right? I should be able to, in the lens case, just pick the one thing and traverse over it, and in the prism case I either have 0 or 1, so I should be able to traverse over the 0 or 1 things. The traversal case is like saying, given any number of things, like any finite container of things, like take your profunctor and lift it up over this container. And it turns out this gives you something that works just like traversal in lens, right? So
traversal is foldable, right?
What's that say?
Traversal is foldable.
So foldable is a superclass of traversable. So traversable, yeah, they're very similar in some ways, but it gives you, like traverse gives you more type structure that you need for some things. Yeah.
In I have a very limited type theoretical knowledge, but in my mind this looks a lot like that optics are really like a higher order type constructor or something like that. It takes these things and lifts or whatever. Something that could be up until traversable, maybe even further if I let it bigger. And then it creates this whole bigger machinery. But in the same formulaic way.
I think that's right. So like, you pick some profunctor, and you get these operations that allow you to lift things like if it's strong. If you can show that it's a strong profunctor, then you get things where you can lift up tupling operations. If you have choice, you can lift up this prisms. If you can show it's an instance of this traversing class, then you automatically get for free this, like, any traversal gives you a lifting operation.
So what's the type then of optic?
So it's this, right? So in general, with like constraint kinds or something, right? We have some constraint C that might be like strong or choice or something. We can say for all profunctors that satisfy this thing, I want a lifting operation.
Great.
Okay, so you can pick any class you want, and you get some notion of optic, and they all compose in nice ways. And I'm just saying here that there's a couple of extra things that you can do. Okay, and they all, in some sense, like amount to identifying big structures as isomorphic to some data structure that's in some big closed family of data structures, like sums and products and things. Yeah. So.
Could you explain what's going on with that SEC line?
I'm going to go through these. No, I was struggling for notation a little. I guess I could just I'll go through it. Sorry, just one second. So if you pick traversing, you get something like traversal. Okay, so this traversing thing is like saying you can lift up your profunctor over all the elements in some traversable container. Okay, Great's pretty interesting because nobody sort of knew about Greats until they did until the profunctor machinery was worked through, and then people said, well, we have this class called closed. I wonder what happens if you stick closed in here. What does that mean? And they worked through it, and Russell O'Connor gave a nice blog post explaining sort of like the various presentations and like what it would look like in the Van Laarhoven presentation. And it's a little bit weird, but so closed profunctors give you this way of like lifting over. Functors where sort of like you have like, I guess, some key, like some x, and it's sort of like keyed by x, and for every x you have a value. So you have like this sort of like, I call them combs, right? So you have like a comb of like various a's of some finite comb. Yeah, so it looks like a comb, right? You have like a bunch of a's on the like leaves of a comb. Like the naming is really bad in general.
To me, that suggested of diffraction gradient, like right out of straight out.
Oh, comb. Yeah. So people call them various things like Napierian containers or something. But the point is you have like some key space x, and it looks like a mapping from the key space into values, right? So closed gives you this thing called great, and great is a way of identifying like things in the leaves of these keyed data structures. And these actually turn out to be quite usul. Like a little bit like dictionary. Well, not quite dictionary, because you have to have, the A has to always be there, right? With a dictionary, there might be like a key missing or something. Okay. Like this is where your key space is fixed, and you always have a value for every key. So it'd be things like pairs, right? Like a pair of A, where you pick Boolean, and you can say, okay, I have a value for true and I have a value for false. Okay. And you can like lift up. This turns out like, I ended up using this for something where you have this like notion of working in parallel, right? Where you have a bunch of these things for these various keys, and you want to apply this AB at each of the points in parallel. It's interesting, but Lens doesn't have this, right? Like this came out of the profunctor stuff. And then this SEC is like the oldest of all of the Lensy things, which is structure editing combinator, which is based on a bunch of blog posts by Connell Elliott. And basically, the constraint here is like that you just pick P to be the function arrow, right? So this tilde means is equal to, right? It's the constraint that just says P always has to be the function arrow. So if you look up the blog post by Connell Elliott, then the type of this thing is a function from A to B to a function to S to T, and it just fits in nicely, right? Like it turns out you can just pick some constraints such that this fits into the hierarchy nicely, and it composes with other stuff. So yeah, the set of all the optics is pretty rich, and you can do a lot. You can do a lot of things with them. So this is the table, right? So you have isos, lenses, prisms, traversals, grates, and affine traversals. They all correspond to some constraint that strengthens the profunctor constraint. And they all identify this big data structure S as being isomorphic to some data structure that has an A in it somewhere. Okay, so lens just says, ISO says S and A are just isomorphic. Lens says S is isomorphic to a tuple, and one of the things in the tuple is going to be A. Prism says the same thing with the sum. S is isomorphic to a sum. One of the summands has to be A. Traversal says S is isomorphic to a finitary container or traversable container of A's. Grate says that S is isomorphic to a function from some key space X to A, like this thing that I call a comb. And then affine traversal says that S is isomorphic to either a sum of a tuple, essentially, right? So this is like your, affine vector space or whatever, right? So you have, A plus X times Y, or A times X plus Y or something like that. Okay, so you asked about the pros and cons of the different approaches, right? So the main pro for me is that like the API is consistent. It takes you a little while to get your head around it all, but once you get the profunctor stuff, it's it's all very sort of clean, and it's easy to sort of think about these ideas once you get the basics. One interesting thing that you can do with profunctor optics that is not possible, as I understand it, with van Laarhoven optics, is that you can generalize the idea of like turning an optic around. So if you have an isomorphism from A to B, you expect that you should be able to turn that around and get an isomorphism from B to A. Okay, but the operation in the profunctor lenses presentation like generalizes to other stuff, right? So you can take a prism and turn it around and get a review or something. And you can take a lens and turn that around and you get something else. And yeah, so there's lots of operations like the closed thing that came out of the profunctor stuff that was not immediately obvious in the van Laarhoven presentation, I think. And this inversion is another one of those. And because the types are more general, right? So the profunctor machinery applies to any profunctor you can pick. You can apply your optics to more structures. Okay, if you can just find any strong profunctor, you can apply lenses. If you find a choice profunctor, you can apply prisms, etc.
That's because more things are profunctors than are what?
Than are star F for some F. So I said before that like the van Laarhoven stuff, like you get the van Laarhoven presentation if you pick your profunctor to be star F for some functor F. So not every profunctor is of that form, which means that you can apply these optics to more profunctors than you could apply to star profunctors. Yeah. Okay, so the downsides are, if you're familiar with lens at all, there's this thing called an index traversal and various indexed optics. The story for that in the profunctor version isn't quite as good, but that's relatively little used. So, I mean, I've not really used it for anything actually, so I don't tend to worry about that too much.
That didn't mean anything to me. What is an indexed optic story?
An index traversal, for example, is something like a traversal, where you can say, go and do this operation at all of these points in this list or something, but in doing so, you get the index at the same time, right? So you can say, run it on this first element, and that's element 0. Now run it on the second thing, that's element 1. And as you're doing your traversal, you get access to the index. So it's just like a regular traversal, but where you get index information as you go. And that's not quite as pleasant in the profunctor approach. In the sense that you don't have as many nice operations to apply.
So is it like, in some sense, you don't know how you got there? You're just there?
Yeah, exactly. When you're in the middle of a traversal, yeah, you sort of like, you don't get to know like what index you're at or whatever.
So you can have access to the previous one when you're moving on the current, right? So
yeah.
You can count how many. Okay.
So there are indexed traversals in the profunctor version, but they don't compose as nicely and they don't have as many operations that you can write. So it's like a minor downside, but it is a downside.
We're not supposed to use indexes, right? So
right.
And so they usually like, this doesn't let us cheat.
Yeah. And the other downside is just one of performance, right? So if, like, for example, if you always have to like go to and from some traversable container, that's kind of an expensive conversion, right? If I have a map or something and I have to like, maybe I have some data structure like, you know, a tuple, a bunch of nested tuples or something, and I want to traverse that thing. Well, in order to traverse it, I have to like turn it into something that has a traversable instance, and that incurs a cost. You know, going to and from that data structure has a cost. So there can be a little bit of a performance penalty depending on how you write these things up. Anyway, so just really quickly to wrap up, here's a real world example of this put to use, right? So I said, this is a good thing to have in your toolbox as a Haskell developer, because if you can think of any profunctor and you can give some of these instances, then you can get lifting operations for free, right? So it's like monad or applicative, right? If you can show that your thing is an applicative, then you get a whole bunch of functions and combinators to work with that applicative, because the standard library defines functions that work with any applicative, right? If you can show that it's a monad, you get even more. So for each one of these things, we get more lifting operations and more things we can define to work with our profunctor, right? So I wanted to define a type of user interfaces. So I defined this, did I get this the wrong way around? I think my A and B are switched here. Sorry, I did this kind of last minute. I think this A and B should be switched. Is that right? Yeah. They're the wrong way around. Okay. Anyway, so let's say you want to define some UI type, and we have a UI and it has some state inside it. Okay, so a way you might model that functionally is to say, okay, well, given a state, you're going to put it on the screen by producing some widgets in the I/O monad. But you're going to want to update your application, right? So when you make some changes and click buttons or something, you might want to change the state. So I'm going to give you a function that takes a state and does some work in I/O that you can call inside your I/O action to update the UI. Okay. Well, you know, we might animate it like this, right? We take a UI and we give an initial state. We can define this sort of loopy function that takes the UI and runs the UI function and passes itself recursively, right? So if you give me a new state, I'll give you, you can run the animate function again on the new state. But it calls this function with the initial state it's given, and then it just renders the widgets to the screen or something, right? So you can imagine this might be like a sort of way of modeling UIs functionally. Well,
wait, is that a loop or that just runs once?
Well, it's a loop because animate calls itself here when the user gives some new state or something, right? But you can imagine like wiring this up to like actually make a UI go, right? And this is.
So it looks like it never gets to the second statement.
It's a callback.
It's a callback, yeah. Yeah, so it provides animate UI to this function here, right? Point is, we can write something with this type that like wires all this stuff up to like handle the event handlers and things. Like this gets rid of a lot of the details, but there's one of the PureScript UI libraries uses this. This is like the approach for the entire library, and it works really nicely. So. All right, so this is an invariant functor, right? Like state appears in both positive and negative positions here. So we said if we have an invariant functor, we want to split out the two type arguments that represent the positive and negative occurrences. Okay, so I got these backwards, like I say, but A is going to be my negative occurrences and B is going to be my positive occurrences. Okay, and then I just go through and try and define some of these type classes for this thing, for this UI type, right? And it turns out it's all of these things, right? So what does that give us? We hope that's going to give us a lot of lifting operations, right? But here's a couple, right? So any lens, so first is a lens. That means that we can take a UI that for some state and give me back, and it'll give me back a UI for some bigger state that works on tuples, okay? What does that mean? So like in a UI case, that means I'm taking some widget that has its own little piece of state, and I'm going to like put it in a corner or something, or like divide the page in two, and I'm going to have a tuple, the left component of which is the state for the left. The left component of the state is going to be the state for the left component, and the right hand component of the tuple is going to be the state for a right hand component, and I can just sort of box off this widget and sort of stick it on the screen, independently of the application that runs in the context of this bigger state, which is a tuple. Does that make sense? So these basically correspond to like typical sort of operations for combining user interfaces. So like I used to use like knockout.js, right? And I don't know if anybody's used it, but like these literally correspond to like 3 of the like keywords in like the markup language for knockout.js, right? This one allows you to sort of identify a little bit of the state that like one component is concerned with. This one corresponds to something a little bit like tabs, right? So this is like saying, I have some tab that has a state, and I want to build it into a tab application that it can have 2 tabs, right? It can be on the left tab, in which case I'm using the state that you gave me, or it's going to be on the right tab, in which case I'm going to use some other state. And then I can do things like data lists. Okay, so I can take traversing, and that lifts up over some traversable container like a list. So if you give me a UI that has some state type, then I can lift it up to a UI whose state is an entire list of those things, and I'm going to render one widget for every element in your list, right? And I can do things like when the user clicks a button, I can have my traversal go and wire all the events to the correct element in the list and update the right piece of state and all these nice things. Okay, so I think that's it. So pointers, like you can do some pretty interesting things with these. Like as long as you can express your data structure as one of these classes or many of these classes, you get all of these nice operations, lifting operations. So you know, it's a nice abstraction to have in the toolbox, in the same way that a lot of these other abstractions are, like applicative and monad and all that kind of stuff. So that's it, unless anybody has any questions. Sorry, it went on a little bit. Yeah. Any questions? Any questions, or wrap up?
With the UI example for this, so this sounds very Redux-like, but much more principled and mathematical. But I think it's I almost think like it's the same sort of idea, right? Where this big bucket of state, and you sort of compose bits, bits of it.
Minus like the sort of, well, this I mean, in the Flux type approach, you think of this as like your dispatcher or whatever, right? But the thing you're missing is like I think it's called the store or something in Redux, right? But it's pretty close, yeah.
Anyway.
The store is like, they have some mutable store, I think, or something, but we have like this immutable store, or our state gets explicitly passed to a callback or something. But yeah.
So one thing that doesn't seem to work super well there is when you want to pass bits of the state to multiple parts of the UI. And I think the types here specifically don't allow that, because you sort of take the A out of the S.
Out of the tuple? Yeah. So I built things like that with this, and what you end up having to do is like, so this is one way to compose, right? You can apply the lens, and you can get a new UI. Another thing you can do is, like, the lens is a data structure, right? So you can pass the lens in as a function argument to the UI component and say, when you need it, apply it. Otherwise, I'm going to give you the whole state. So when you have a situation like that with shared state, you can do something like that where you can say, I'm going to give you everything, and here's the lens that you can use to apply to get out the bit that you're interested in if you need it. Yeah. So yeah, it can be an issue, but there's ways around it, I suppose.
Which PureScript UI library?
There's 2. There's it's here. The original one was called PureScript's Optic UI. So it's this thing. So trying to find a good example, right? So here's it looks like this, right? So let's say you want to form something whose state is a tuple, then you can. So there'll be some lenses somewhere, right? Here's a lens, right? So he's just applying a lens to a UI for a string, and he's getting back a UI for a tuple of 2 strings, and you can get like 2 text boxes next to each other that like update each other independently. So then, I had some UI library that I was working on, and I saw this and basically just nabbed it because it was quite nice. So there's another library called Thermite that I maintain that uses the same approach now. So, Any other questions? Good. All right. Cool. Thank you.
Thank you.
I have a way to feed people who eat uncooked food, because I have uncooked food already. In order to also have a way to feed people who eat cooked food, I need to cook the food.
That looks like covariance to me, not contravariance.
So it's not necessarily that I have a way to feed them. It's that I can eat the food, right? If I can eat, what was your example? I'm sorry. If I can eat cooked food, then I can eat uncooked food because I can cook it and then eat it.
I think it might be helpful if you could just write out the specific type of CMAP on the board with the customer.
Yeah, let's do that.
There's a whiteboard.
Oh, good. Good idea. All right. So.
Maybe, so the camera, if you rotate the board, it'll be on the camera.
Well,
You've got an audience to worry about too. Never mind.
Yeah, this should work.
Okay.
So if we have some contravariant functor C, okay, but we're just going to pick that to be customer, okay. So.
The one you wrote on the board is covariant.
Yes, it is. I'm sorry. Thank you. Okay. So I have a customer B. Customer B.
Yeah.
Okay, so let's pick this to be a cooking function. Okay, so this is, we have some uncooked. Okay, then I should be able to take a customer who is willing to eat cooked food, and you should be able to give me a customer that is willing to eat uncooked food.
Yeah, so how do you do that?
Okay, so you take the food, if you're given a piece of, so let's write out the type of customer. Food is food to, let's say, some action, IO action, okay? So we'll fill in the blanks, okay? I'll just call it un and co or something.
So the customer is not a wrapper for food, it's a function that transforms food into an IO action.
Correct, yeah. Okay.
Wait, so un is what?
Uncooked to cooked.
Okay.
Then I can, if you have an action which will accept cooked food, then I can give you an action eat which will accept uncooked food, because I can cook, and then I just compose these two things. It's just function composition.
So the type parameter is describing a requirement and not necessarily what it's spitting out. That's why we can do it? Is that why?
So, not sure how to explain this again. So maybe I need to skip ahead a slide or two and just continue, and it'll become clear. So the sort of the key example is like the function arrow, right? So the function arrow has two type arguments. It has its arguments and its return value. Okay, so we say it's covariant in its return value. Okay, because if you have a function which returns A's and an A to B, then I can just compose them and I get a function that returns B's. Okay, but it's contravariant in its argument, because if I have a function from A to B, I need an A and I have to map this way, right? I have to have a sort of a Z to an A to a B, then I can get a Z to a B. So it maps the other way.
Okay, can you draw that?
Yeah.
There's probably some laws that would make this more clear, right? Between covariant and contravariant.
So there are contravariant functor laws, which is just the functor laws, the other way around. This is sort of my archetypal example of a contravariant functor. So it's sort of trying to think of a better one, but I mean the function arrow is sort of a typical one. Let's see. So I have A to B. Okay, so let's say I want to write an instance of functor for the second argument. Okay, so let's say we fix the first argument, and we want to show that it's functorial in this piece. Okay, Okay. Then, well, let's give a type signature to fmap. Okay, so fmap says if you give me an x to a y, then I give you an f of x, so that's going to be a to x. Okay. Then you give me an f. You'll get an f of y back. Okay, so that's an a to a y. Okay, so we need to implement this. Well, that's just function composition, right? If we call this f and this one g, then we do f first and then we do g, then we get a to y. Okay. So I'll write that. It might be the other way around. No, that's correct, right?
Is that the dot?
That's composition, yeah, sorry, dot. So let's say we want to write a contravariant instance, okay. But now my claim is that it's contravariant in this piece, right? So, so let's write out the signature again. So we had CMap, and we needed an A to a B, and then a C of B. So a C of B is a, oh, I'm sorry. Alpha renaming, my head is not working. All right. Next to a Y, let's say, and a C of Y, so that's a Y to a B, and you need to give me a Y to an A.
Wait, a C of Y is a Y to B?
So we're just plugging in, this is C of
Okay.
Y, and we're just plugging in Y here. Oh, this is an X, I'm sorry. Okay, and again, this is just function composition.
But you compose them in the other
That should be x to b.
Yes, it should, thank you. Okay, so this is just function composition again, right? If I have an X, and I have an X to a Y, and a Y to a B, then I can put the X into the first function, get a Y out, the Y in the second function, get a B and return it. So I think this is like...
Okay, so you're just composing them the other way.
Yeah, so this is flip compose.
Yeah.
Okay, you can always extend a function by applying. You can take your function and sort of apply it on the right and extend the sort of chain of functions, or you can take a function and apply it on the left. But in doing so, you have to flip the type arguments. Does that make sense?
This is just the generalization of the customer.
Right. So exactly. So a customer is a function, right? Here we're just fixing B to be IO.
Okay.
So now we just have one type argument. I was saying, so this filling here is the one on the left of the function arrow. That's this one. It's contravariant. So we're saying we're contravariant in filling. Okay.
Cool.
Any other questions on that before I carry on?
I can't imagine where I would use contra.
Right. It's not as common. It's not nowhere near as common as functor in my experience. It's more common, I think, in the form of a profunctor, which is the next slide. After this one. An intuition for this is, so we already covered the function arrow, right? So we jumped ahead a little bit, but a functor is something where the type argument appears only in what we call positive position, okay? And something is contravariant when its type argument appears only in negative position. If you have a mix, you can't be either, okay? So what does positive and negative position mean? Well, something is positive if it appears on the, let me get this right, left-hand side of an even number of function arrows. Okay, so let's write this out. So it's easy to see when see it for the function arrow. Okay, so here's A to B. Is this? Well, I'll tell you the answer for these, and then we'll carry on. Okay, this is a positive occurrence of B. And this is a negative occurrence of A, because we have A on the left-hand side of one arrow, okay? Would anyone like to guess what the polarity of C is in this type? Positive. B? Negative. A. Also negative, right? And if it's not clear why A is also negative, think of it like this, okay? You can always curry these things, uncurry, actually. Okay, let's do a more interesting example. So we had A to B to C. If I parenthesize like this, okay, this is still positive because it's on the right-hand side still. But but this has changed, right? So in this case, b is negative because it appears on the right-hand side of one function arrow, left-hand side of one function arrow, which is this one. Okay, so every time you go into a function arrow on the left, you flip the polarity, okay? This one is positive. So this went, because I went inside two function arrows on the left, I flipped twice and now I'm positive again. So A is positive, right? So the rule is I can make a functor when the type argument only appears in positive position. So if I want a functor for something like, let's see.
Is there some other definition of positive and negative positions? Because that rule with the arrows, I can believe you that corresponds to something, but I don't really know what it's supposed to correspond to.
So this is Fun with Profunctors. I'm going to be talking about, let's see. I'm going to try and give a bit of an overview of Profunctors first of all, just to give a bit of background. And then the thing I really want to talk about is this Profunctor lenses idea. So if you're familiar with the lens library from Haskell, it's sort of a different sort of development of those ideas. Lenses, prisms, traversals, all those kinds of things. If you're not familiar with the ideas from Haskell Lens Library, I'll try to give a quick primer on lens before we get too deep into this. So the thing that is kind of interesting about this is that I think it gives a really nice, clear presentation of, or at least clearer presentation of the lens ideas. But it hasn't really been developed in the Haskell Lens Library, or as far as I know, in the Haskell library at all yet. So Edward Komet, I think, is a little reluctant to develop the lens library this way because it sort of pulls in a lot of dependencies that are relatively non-standard, like non-base dependencies, like Profunctors, for example. So the way I came to find out about these ideas was by working on the PureScript lens library. And Edward popped up and said, you know, you really ought to take a look at this Profunctor lens idea. You don't sort of have the same set of restrictions that we have in Haskell. So we tried it out and implemented it. It was very clean and elegant, and I think it's sort of like a nice overview of like lens ideas, and I wanted to cover it. But most of the sort of material here is sort of extracted from the Haskell Lens IRC channel and various other places on the internet. There isn't, as far as I can tell, a really sort of clear presentation of this stuff. So you know, hopefully this will serve as a nice introduction, but we'll see. I have quite a lot of material, so we'll just sort of see how much I get through, but please do stop. It's quite dense, so please ask a lot of questions. If something isn't clear, I'm sure somebody else has the same question. Okay, so let's just go through the primers, the prerequisites real quick. So we're going to look at various types of functor. So a profunctor, as you would expect, is related to the functor type class, which hopefully we all sort of know and are familiar with. So a functor is a type constructor f, and you have an fmap function that gives you a function from fa to fb whenever you have a function from a to b. So a good example of this is the map function on lists. So if you give me a function from a to b, then I can give you a function from list of a to list of b, where I just apply that function pointwise at every element in the list. Okay. So people like, you know, analogies for things like monads and functors, and the typical one is a burrito. So I have this burrito functor here, and it's got some type argument, which is the filling. So if you can give me a way of transforming one filling into another filling, then I can transform your burrito into the other type of burrito by taking off the tortilla, applying your function to the filling, and then putting it back in the tortilla, right? So this is sort of our typical, this is going to be our basic example of a functor, okay? As I say, stop me if anything needs, because like I say, this is going to get pretty dense pretty quickly. So, okay, so then sort of related dual idea to a functor is a contravariant functor. So we say a functor is covariant, and we have this other idea of contravariant functors. And if you're familiar with sort of Java and I guess subclassing and these ideas, then you'll have heard the words contravariant and covariant, and they are related. This idea of sort of things being sort of depending in the same way or depending in sort of a reverse dependency sort of way. But so contravariant, instead of having this fmap function, has this cmap function.
So are normal functors covariant?
So normal functors are covariant, yeah, that's right. So covariant just means, so the co sort of, I guess, meaning together, right? Like the arrows sort of go together in the same direction. It's A to B and F of A to F of B. But in the contravariant case, they go the other way around. We flip the arrows on one side, right? So we have an A to B, but now I have an FB, and I give you back an FA, okay? So so a simple example of that might be, like a customer functor. A customer, instead of a burrito where we're wrapping up a burrito, now we're sort of taking we're wrapping up a filling. Now we're taking the filling and we're doing something to it, right? We're going to have this eating action. So I can take this filling and eat the filling. Then the customer type constructor is now contravariant, okay? Because if I can give you a function from A to B, and I have a customer that's willing to eat B's, then I also have a customer that's willing to eat A's, because I can just transform the A's into B's and give it to the customer. Does that make sense? Okay. So this type of functor where you have...
How do you know which... So you know how to go from A's to B's.
Yes.
But does that imply that every B has some A that goes to it?
Not necessarily. So that'd be like, I guess, a surjective function or something, right? I think not necessarily, no.
So then how do you define the F of B to F of A function?
So I mean, here's an example, right? It's specific to the F that you pick. So here's an example, like for the customer. If I have an eat function that takes, let's see, that will be it's an F of B, so that's going to be a B to an IO.
Wait, the filling is A or B?
Okay, so you have to do a bit of sort of substitution in your head here. I'm sorry. Right? So here F is going to be your A to B. Okay, and we've picked. I'm sorry, it doesn't help that this is also called F, but this F is going to be customer, right? So now we have a customer of B, right? So we have a customer who will eat B's, and we have a function from A to B, and I want a customer that will eat A's. So I just take all my A's and I apply F to them to get a bunch of B's, and then feed them to my customer.
Wait. This might be easier.
The burrito analogy doesn't like generalize nicely.
I might understand it.
Yeah, I think
So
Okay.
if you only eat cooked food, and I have some uncooked food, I have a function that cooks the food, then I have a way to feed you.
Right, but that's a function from uncooked food to cooked food. And you're talking about going from a person who eats uncooked food to a person who eats cooked food, right?